Thank you. So first, I would like to thank the organizers, of course, and Viviana in particular for getting in touch with me, and Chiara. I'm very happy to be there, although it's a bit of a strange experience compared to my last visit at the MGH, not to see the front audience, but I hope all of you are doing okay. So I'm welcoming any questions, and I'll try to keep track of them, as Viviana said, so don't hesitate to interrupt me. So we'll go straight into the heart of the matter. So we'll be talking about time perception with the, hopefully can my slide go through? Here we go. I'll first start by acknowledging the young researchers that have worked on the different studies that I will be presenting, and not only these guys up here. And this is the constitution of my current team. We've decreased a little bit since last year. So the problem of time is, of course, a crucial one, and that is one that is cross-disciplinary, that is at the junction, so to speak, between physics with divergent views, going also to the point where time does not exist. And then as cognitive neuroscientists, we're interested in figuring out how the brain is going to map this time or these temporal statistics of events, considering that the brain is this complex dynamic system that is characterized by various temporal scales, but also different temporal dynamics and temporal constraints, and trying to understand in particular the human brain with phenomenologies of time that can range from basic things like distinguishing that there are two events in the world, all the way up to things like planning and planning future, your agenda, and so on. So having mental representation of time that are much higher level. So I will try to illustrate the different approaches that I've been taking with the team to address this question of how the human mind can make sense of time, but I will try to embed this into a lineage of big questions that have been in the field since the 19th century, let's say. So I'm quoting here a philosopher who is a contemporary of William James. And basically, I let you read, but it is indisputable that our consciousness of the passage of time is determined by our consciousness of the sequence of events, time consciousness being nothing more than the memory of a series of successive changes in consciousness. And the interesting part here is basically that if you were to read this nowadays, it would still fit very well with the different theories of time representations or even consciousness. So a century and a half later, this doesn't shock us as being totally inaccurate. Yet in the 20th century, a lot of biologists and cognitive neuroscientists and philosophers as well have thought about the problem of how the brain may represent time, and in particular, the past to future. So the fact that there is an asymmetry in time that we don't necessarily find with space. And so starting from Ashley, that I'm sure many of you know, to Hayek, and of course Randy Gallistel, but also Dennett and Kinsburn, who I think made a good argument for the fact that time must be represented in the brain and not just mapped or directly mapped, by basically suggesting that indeed the sequence of events in the world outside of us is not going to be linearly mapped as a sequence of events in the brain. And so the problem, of course, when we're interested in the psychology is how can we target these non-linearities here, and how do they reveal themselves in behavior? So if we fast forward to 21st century, we still have difficulties coming to terms with this notion of sequence, time, and linear representation. So just in a recent review by Boujaki and Friston, we can read things like the representation of a sequence is not a sequence of representations, which echo a bit what Efron was saying in the 70s. And if I were to reformulate, it's as if we were saying that the consciousness of time is not the timing of consciousness. So basically going to the notion that we need to explain what a representation for time is in the brain if it is not time itself, or if it's not the temporal properties that linearly map to the temporalities that we can observe outside. So this is my challenge for the next few minutes. And I will try to illustrate this with 3 levels. I will go with the first one, which is a very, very low level of representation using flashes and loops and temporal order. And And in the second level, we'll go to mental time travel. And the third one, hopefully I will have time for this, which is on motor timing. So all three of them, to keep in mind that we're trying to target basically this past to future, how we go with this representation that would not be just duration per se, but the actual ordinality of events in time. So if we take a basic temporal order judgment in which we ask participants to estimate the order, in this case here, of a sound and a visual event, that we separate by a variable amount of time, you usually can draw this very nice psychometric curve where on the y-axis you have the percentage of perceiving the flash first, and on the x-axis you have the audiovisual delays that was given to the participant. Now, typically the 50% threshold is being interpreted as the point of subjective simultaneity, which is already a sort of a stretch or an interpretative view of what that threshold is, because rather literally this point means that it's the maximal ambiguity in assessing the order of events in time for the participants. So it's a bit of an interpretative stretch here. Now, what's interesting in using this temporal order judgment is that since about a century, the Tichenor law tells us that when you pay attention to one sensory modality or the other, you're going to have an effect that is called a prior entry, so that you're going to see one before the other, just by paying attention to it. So you have this illustrated here. This is a mock psychometric curve that we've just seen when we don't pay attention particularly to sound or vision. Now we ask participants to pay attention to vision. This means that you're going to have to present the sound before the visual event for participants to now perceive simultaneity. And the reason is that you have to basically caught up with the fact that participants pay attention to vision, so they're going to process the visual event faster than the sound. So now you need to present the sound before the visual event. And when we actually measure this by simply asking participants to pay attention to visual event, we indeed find that the PSS, point of subjective simultaneity, shifts towards negative values. And conversely, if we now ask participants to pay attention to the auditory or to the sound, we will have to present the visual event roughly 20 milliseconds before the sound to actually occur, to be actually deemed simultaneous with the visual event. Okay, so far so good. We replicate what psychology tells us for the last century. Now, what we were interested in is this variability here, the fact that across individual, there seems to be this huge variability. So what we did is to look at the point of subjective simultaneity across participants. And when you look at this, you realize that you have a large distribution going from minus 100 milliseconds, meaning the sound has to precede vision to be considered simultaneous, to 100 milliseconds, in which the sound has now to be delayed by 100 milliseconds to be considered simultaneous. When we test participants 4 times in 4 months, so longitudinally, we realize that the inter-individual variance is much smaller than the across individual variance. And this signifies that over the course of time, for the same kind of experiments, this basic temporal order judgment, participants are quite robust and show basically a bias that is stable over a month. Now, when we do this same experiment, but this time we ask participants to pay attention to vision in red or to audition in blue, what you see is that we replicate again the prior entry results. But what is most interesting to me is that despite being able to modulate their attention to one or the other sensory modality, you do not retrieve realignment of all individuals on the 0 line. So that means that participants that start with a bias are going to be able to compensate a little bit, but not to the point of recovering the full simultaneity of the audiovisual events. So in other words, there is no such thing as the mapping of veridical objective order in the brain, and we are all subject to different biases as to this order. Now, when we test this in the MEG, and I will not go in details because it's a complicated study that would take me too long to really go in details, and I want to move on to other things. What we did here is basically look at the pre-stimulus alpha baseline preceding the presentation of the sound and vision to try and test the idea of prioritization that was put forward by Ole Jensen. And to some extent, this notion of prioritization of information that would be regulated by alpha power before the presentation of stimulus held on in our study, but only when we considered in advance the psychological prior or the subjective bias of participants. So in other words, the differences in power that we saw in the pre-stimulus alpha power were only interpretable to the extent that they were a function of the individual bias. So in this case here, you have the different points corresponding to the individuals. And when we saw an increased pre-stimulus alpha power in auditory cortices for participants that required a visual event to be presented before a sound, then we indeed had a following of the structural bias so that participants were incorrect in reporting their perceptual event. So this is a bit of a complicated story. This is in line also with the recent work that suggests that you may actually have modulation of the sensitivity in perception due to pre-stimulus alpha power. And this is published work, so I will leave it to you if you're interested in this. Okay, so this was the very basic part in terms of the order, saying that already endogenously the brain is going to be, each individual brain is going to be basically biased toward one order or the other, which to some extent could seem trivial because we all have different anatomies and different connectivity. So if you have a simple model looking at the latency of these measures, you would expect to see some inter-individual variability. But strangely enough, this question was not raised in psychology for the last century, also considering when we considered only this temporal order judgment part. Now we're going to go to the totally opposite in terms of complexity and level of analysis by going into the conscious time arrow. So looking at mental time travel, and I'm going to show you the kind of paradigm we did here. So this is what we did with Baptiste Gauthier. The basic question that we asked here was, can we consider the time dimension in the way, or can we approach the time dimension and the way the brain is going to map it the same way we do it for space? So of course, you have two ways in which that coexist in the brain as to how you map space. One, which is called the path integration, which is more of an egocentric or self-reference way of mapping space that you can traverse. And then the map-based navigation, which is also the allocentric, the fact that we have a map possibly in the brain that we can navigate or that can help us do some route planning. Now, of course, it's fairly easy when you do a path integration or when you do rat studies in a maze, thereby the body is going to move in space and there is going to be a strong correlation between space and time, the duration, because of the basically modulo the speed. That is, they're going to be a confound between these two dimensions, and it's very difficult to disentangle them. Now, when we think about planning time or temporal reasoning or mental time travel, which I think share some commonalities, the idea is that you have a mental representation of time, a little bit that would be akin to this sort of representation, and in which you can actually mentally move around. And so this is what we try to test in this series of experiments. Now, we found this wonderful series of study by Shaharazi, who I think was visited Harvard not so long ago. And he had used a episodic memory task in which he asked participants to provide some events that were important in their lives. And then he asked them to imagine themselves in the past, 10 years in the past, 10 years in the past, and then to rate where their events, for instance, the car license, September 11, and so on, were with respect to where they were mentally. So, for instance, was the car before or after where the person was mentally, and did the same thing in the future. So what he described using this task were two main effects. The first one is what he called the absolute distance effect, in which when you do the task without self-projecting in time, so you stay now and you order events in before as being before or after where you are now, you have this particular reaction time and an error rate. And as soon as you self-project, you're going to increase your reaction time in both direction, past and future, and also increase your error rate. This is the absolute distance effect. And these are commensurate thus with the self-projections, okay? On the other side, we have the relative distance effects, and those are with respect to the events, with respect to where you are mentally. So what is being shown in this graph here is that the reaction time is going to go faster and faster the further away in the past and the further away in the future the events are with respect to where you are mentally. And it's with respect where you are mentally, because you see this effect when you don't self-project, but you also see this effect when you self-project in the past and when you self-project in the future. So these are the relative distance effects. Now, what we did is use the same sort of paradigm and the same sort of approach, but this time, instead of using episodic memory, we used historical events. So this study was conducted in 2012, meaning that the present time is 2012 and not 2020. Here you have the historical events that occurred in the past and that were supposed to occur in the future. You have here the example of a Dibank Dam building in India, which was a future event in 2017, and that was supposed to occur but did not. So it was a false event. But basically, what you have here is the list that was provided to participants with a few description about the event itself, the date, of course, and where it took place in the map. And what we try to do is to distribute all of these events, both in time and space. So in a grid matter, we had 36 possible events. And the kind of experiments we did is very similar to the one I just showed you. So this time we asked, but we used the 2 dimensions. So we used both space and time. So participants could be asked to project themselves in time. Everything will be in red. So here, for instance, 9 years ago, then we were telling them that they would have a temporal order judgment to do. So the question was before, after. And then we were presenting them with the actual historical event. And from there on, they had to say whether this historical event was before or after where they were mentally. We did exactly the same with exactly the same events, but this time in space, where here, for instance, they had to imagine themselves in Cayenne. They had to, but this time they had to tell whether the event was west or east of where they were mentally in space. Okay, so we did a series of experiments, first behaviorally, to make sure that we could recover the same sort of behavioral effects. So here you have the reaction times on the left and the error rates on the right. Again, everything that is in red is about mental time travel. Everything in blue is mental space travel. And you can see that when you project yourself away from the now, so in past or future, you increase reaction time. Same thing for the spatial projection, and you increase the error rate. So the first absolute distance effects with this data, which are not episodic memory, are actually replicating what was found by Shahar. And then we also observed the relative distance effects, thereby the reaction time decreased linearly or logarithmically, because both of them fit the data very well, so we couldn't distinguish. We went with a sampler. And so the further away you are in time and the further away the event is in space, the faster you're going to be in telling whether they are before, after when you do a mental time task, or east-west when you do the space task. And this is observed both in the now and in each of the possible projections that we tested. Now, one of the idea, of course, because there's a lot of work showing that you may have interferences between time and space, was to look at whether we had indeed interferences between time and space. But in fact, we did not find very big results or very dramatic interferences effects. For instance, the behavioral cause that we found between dimension was still the behavioral cause that we found within a single dimension, so within time or within space, was still much higher than what we could find across dimension. And by this, I mean that when you projected yourself in time, you were, and doing the task in space, you were not really, your behavior was not as bad as what would be expected on the basis of an interference effect. And furthermore, going against this notion that time and space are totally mapped in the same manner, we actually observed a switch cost, so that when the preceding trial asked you or asked the participant to project themselves in time, and then they had to switch to mental space travel task, then they had a behavioral cost in switching dimension. Okay, so this is for the behavior, ensuring that there was replication of previous work. And now we are going to the fMRI, where we wanted to see whether the networks and the brain regions that were implicated in those two tasks were in full overlap or show some distinctions. For this particular fMRI study, we also use a control in which we ask participants on the exact same event set to provide a valence judgment. So the order and the whole sequencing of the task was identical. Only the dimension of judgment was different, and this was used as a stringent control to make sure that we control for the memory, cost, and over general executive process in the task. All of the tasks were exactly the same for fMRI. So the brain regions that we found to be implicated in judging this temporal or spatial ordinality versus the control is depicted here. You can see that there are quite some nice overlap, which is here represented in purple between the time and the space tasks, and some slight differences, notably for the frontal engagement that is much more robust in the temporal task. So the core network is listed here, and it's pretty restrictive with respect to the time and space task. Now, if we go in more details, when we look at the space versus time, now we see that there are large differences across the different regions. And in particular, the spatial dimension seems to recruit much more the parietal navigation system, which is quite well known to be engaged in both real and virtual maze experiments. And whereas for the time dimension, which is depicted in red, you can see that you have much more frontal engagement. You also have, again, some of the overlapping, which we go through in the next slide, in the parietal regions, but essentially you have more of a prefrontal cortex being engaged here. When we look at the specificity of the self-projection at the top and the egocentric distance computation at the bottom, namely by egocentric distance, I mean here the mapping of the events with respect to where you are mentally in time or space. So in the self-projection part, you can see that, again, you find mostly the brain regions that are implicated in the time task, notably with the prefrontal cortex engagement, and you retrieve again this overlap in the angular gyrus region with the space, but you don't see much of the regions engaged for the spatial task. It seems that it's in the ordering itself of events that the spatial regions and in particular the precuneus and different parietal regions seems to be much more engaged, and this time you see much less engagement from the time tasks. So there seem to be some different dynamics here going on in this task. So one of the regions that seemed to be very interesting for between the two tasks in overlap is the one that we called IPL angular gyrus, because we couldn't really pin down exactly which it was, although it was in congruence with prior work that looked at things that are quite abstract, like the distance, basically the distance to self, including the distance to self in social terms, for instance, with this study by Parkinson et al. But otherwise, it's also seen with studies looking at this spatial navigation and temporal navigation. So this region was engaged in all effects, all behavioral effects that showed a distance to self, egocentric and self-projection included. So overall, we realized that the findings that we have here with the fMRI are quite consistent with what we can find in the spatial navigation literature, with in particular the transformation of allocentric to egocentric mapping in space that are engaging very similar regions, precuneus, retrospinal cortex, for virtual navigation, as we do here with purely mental navigation. So Again, there was no, during the task, participants did not see a map. Everything was basically mentalized space. With respect to the mental time travel, the regions that we see that are engaged seem to be more of the executive control regions. They do not directly or easily, they cannot be easily be mapped to the kind of networks we can see involved in linguistic systems or in arithmetics. So it doesn't seem that this system alone could explain the fact that probably phenomenologically you try to verbalize these events in your mind to try and solve the task. So much work is needed here. Now, on this particular set of results, we were, of course, quite intrigued by the fact that there was not so much overlap between the two tasks. I mean, in time and space between the two dimensions, despite trying to fine-tune the task in such a way that they were so equivalent, only the two dimensions differ. But the thing that was a bit disappointing also was that there was no difference between past and future. So I started the talk by mentioning that a major difference, at least for the phenomenology of time and space, is that time is asymmetrical. There's a past and a future, past that occurred and a future that did not. And so we were hoping to find indices in the brain that would tell us something about that. But with fMRI, we failed to find it. A second thing that we failed to find is a large engagement of the hippocampal network. But we realized after the fact that the field has also a hard time to pin down the hippocampal network. So we figured that probably it might be a problem of dynamics that the fMRI is not sufficiently good to capture. So we went to MEG to ask the question about this ordinality. And we did this very same experiment with MEG. So maybe I will not go through all of the details results. I mean, we did find some markers for self-projection, but they're a little bit different whether you look at time and space. So I will move on to the core finding, which is more complicated. We did do some hippocampal structure source reconstruction using MNE Python with volume source reconstruction. You can see we did find with MEG that hippocampal activity was there from the start. So on every trial, we could see that there was a significant increase from the baseline in activity in different hippocampal structures, including entorhinal cortex. But none of them at this stage of the stealth projection were selective to either the dimension, so whether you go in time or space, or to the direction of your projection. So whether you go in the past, future, or whether you go east or west in space. So it seems that hippocampus is engaged in this task at that level, but not before the event retrieval. So the key finding for this MEG study is the following. What we reasoned is that in this task, what we ask participants when we ask them to self-project is essentially with this red arrow here to translate themselves on this grid map, right? So here you're in the present. If we ask you to self-project in the future, you're basically going to realign yourself here to the present, and all of the events are going to now be shifted towards where you're supposed to be mentally. And same thing, and same thing if you project yourself in the future. So what we did here is basically realigned all of the events with respect to where participants are supposed to be in their mind. So not on the physical now, but on the mental now. And we subdivided all of these events into 8 bins. And the crucial point here is, of course, that if we follow this translation, when you are in, for instance, this event here, that would be the past for the now, becomes actually the future once you've translated, right? So we blur basically the boundary of the physical dates by averaging the events based on this mental map. And from this, we try to look at where in the brain and how in the brain we would find a marker that could help us tell whether events, when they're being retrieved, are past events, future events, and how far away they are from the mental now. And so this is what you have here. The gradation is the gradation from past to future, with past being the darkest and the future being the lightest. And you can see here that we have a reversal of polarity in the response, as well as a difference of amplitude, an incremental amplitude as a function of distance. So the further away you are from the now, the larger the amplitude was, either negative or positive. When we look at this in source reconstruction, so that's how it looks at the evoked response level. We are about 500 milliseconds following the event retrieval. This is how it looks like on the scalp. And when we did source reconstruction, but not accounting for hippocampal structures, we found the middle temporal cortices being implicated. So there's more data afterwards showing that hippocampal structures are in fact implicated. And the second marker that we found is also the distance that is not telling us anything about past and future. So an absolute distance, where this time you have an increased amplitude the further away you are from the mental now, but you cannot tell whether you past or future. So there's a symmetricality involved. And again, we are quite late following the event retrieval. We're roughly at 800 milliseconds. It's again an evoked response here. And the structure that are being engaged are more like parietal and retrospinal cortex in this case. Now, what we did, because we saw that this middle temporal cortex seems to be implicated in these distance effects, we went back to the data and tried this volumic source reconstruction and performed the same analysis, but this time in the different structures. And we found that the remapping and accounting for the existence of hippocampal volume in the source reconstruction model now suggests that the effects, these linear effects as a function of a distance, can be seen also in these hippocampal structures and much less in middle temporal cortices. We did exactly the same analysis for space, and I'll move on this. We found in the cerebral cortex paper, we also found both absolute and sign distance effects. So the sign being able to tell you whether you're east or west, and the absolute distance, again, telling you how far you are irrespective of east or west. Both hippocampal structures were also implicated in this case. And we also found some retrospinal and parietal cortices implicated when we looked at the cortical responses there. So basically doing a simple, okay, and this is to say, and this slide should have been before, that this is consistent with prior literature looking at distance effect in the hippocampal structures, but this time drawn from more memory based, which is in agreement with the fact that we observe these distances after the retrieval of the events. And so during the mapping, at least that's the hypothesis, during the cognitive mapping of time and the placement of those events with respect to the egocentric mapping in time. So the idea of this series of study, and that we're still pursuing, is that indeed the sequential order of events in a cognitive map that is spatial based or temporal based in this particular task would rely on very similar algorithms, as we found markers for both egocentricity, so the fact that you actually remap events with respect to self, as well as distance effect, how far events are, whether it's a time dimension or the spatial dimension, and the fact that we have order computation, that is the remapping of these events with respect to the self. But, and essentially both from the fMRI and from the MEG, we can conclude that the cortical implementations are rather different, simply because with the fMRI, we found very different structures being implicated. With MEG, we also found different structures, but also very different latencies at which these effects occurred. So the idea of basically the analogies that we do between time and space would be at the algorithm. The argument here is that the analogies we do between time and space are at the algorithmic level, but not necessarily in the structure implicated beyond at least the hippocampal structures. Is there any question at this stage of the talk before I move on to the last study? Okay, I don't see at least any on my questions, so I'll move on. Okay, I'll go to, so we went to the hardest, more complicated series of study right now, and we'll go to a task that is much simpler, but the analyses are a bit more complicated on this one. So what we ask with this next series of study is how you can, whether you can actually generate time, so generate a duration, self-generate, produce a duration, and whether you can have access to your own estimates of durations or own estimates of time. So the task is very easy. We basically asked participants to press a button to indicate the duration that they would produce, and we asked them to produce 1.45 seconds. So you have a design here. This is what we call the first order judgment, and you see the 2-button press. Now, so we did not train participants to do this, although they did receive feedback on some percentage of the trials, depending on the blocks, roughly about 15% of the trials. And then the part which is more novel is that we ask participants to also self-estimate or to judge whether they considered their duration to be too short, too long, and by how much. So not about it, it was not a confidence rating, it was another magnitude rating, but this time on what they produced. And this is the part you see here. Now, the first thing that is quite interesting to observe is that when you ask participants before or without really training them hard on what 1.45 seconds are, you actually realize that they have pretty nice distribution centered not so far, and it's nice Gaussian distribution. When we asked them to estimate whether they were too short, too long, and by how much, we actually found a very strong correlation between the metacognitive judgment, or the second order judgment, which is represented here as a z-score on the y-axis, as a function of the first order judgment, also represented as a z-score, across all participants. Here you have some details about individuals. So you have 4 individuals here as well. Same plotting mechanism, so metacognitive judgment as a function of the first order, the duration produced. You can see that some participants, like this guy, were very, very bad at self-estimated their production, whereas some were very good, like this one here had a very good estimation. And this is the same kind of correlation between the production of a duration interval and the metacognitive judgment over time. So you can see that the fluctuation is quite congruent with each other. Now, we did this experiment, of course, running MEG. The first index that we found and replicate from previous literature is that during that task, one marker of the accuracy with which you're going to produce a duration can be found in beta oscillatory activity, which is here represented as a function of whether participants were short, correct, or long on the task. You can see that there's alpha increase, but what really changes as a function of a duration is the beta here, which becomes stronger and stronger the longer you are. And here you can see the quantification of the beta power as a function of the first order judgment. Now, this was shown before in temporal production task as well as in perception and duration perception. So this starts being quite a robust indicator of duration estimation, beta power increase. Now, what we were interested in is the marker that would help us understand the metacognitive part. And for this, Tadeusz, who's the leader on this series of study, applied a demixed PCA to the beta power that we see here. So he took the beta power and then for each participant in the sensor space, devised the short, correct, and long, and applied the demixed PCA to the matrix. So this is the kind of results we have for 2 distinct participants here. The color codes for whether they were short, correct, or long on the trials. Oh, I'm not sure. Okay. All right, so this is what we call now the beta state space trajectory. And you can see in these 2 participants that one has all three of them first can separate between short, correct, and long, but their level of separation is slightly different between the 2. So this one shows trajectories that are much more easy to separate than these participants. So now what we were interested in is that if these trajectories are of interest to our metacognitive system, then could we deduce from these dynamics whether participants are going to be good or bad in their metacognitive judgments? And for this, we basically apply this analysis to every individual and look at whether the distance between trajectories was a good predictor of metacognitive ability. And this is what we found with a series of different quantifications. So whether we looked at the Euclidean distance, whether we looked at it from different sensor space inference. So on the y-axis, you have the metacognitive inference as a function of the Euclidean distance. And the squares here, this guy here is participant 6 that show the largest distance between the 3 different conditions. So basically, the idea here is that if the beta states dependent trajectory or the beta activity in the network can be read out by a metacognitive system, then you can actually infer whether you were short or long on a particular trial. Now, the idea here is quite different from the traditional implication of neural oscillations in timing. So typically, when we think about neural oscillations for timing, we think of them as a clock model or as a sort of a timer. Whereas here we conceive of the beta oscillation or beta activity as a release of inhibition. So you basically time by virtue of passively releasing from inhibition. We're in a motor system, so the argument is that when you're going to establish your forward model to press a button, one of the variable might be the beta power inhibition in the network. And so here what is being represented is that the stronger inhibition in the network, of course, the longer it's going to take to the network to go back to baseline. And by virtue of doing a motor timing task, you're going to be longer in estimating your duration. Whereas when you have a very small inhibition, you're going to take much less time to go back to baseline, and this defines, in a sense, your motor timing. So the idea is that this beta might be a marker of an internal variable that predetermine how long it's going to take you to make the second press here. Now, so these are basically a marker of the first level accuracy and the metacognitive judgments. We were also interested in the precision with which participants did this task. And for this, we looked at cross-frequency coupling, as many studies have suggested that oscillators may be of interest for timing. So the two maiden power that we found in this experiment and during the timing, during the first button press and the second button press, was the alpha and the beta power, which I think you could see already in the time frequency depiction. And you can see here on a per individual basis in the Ph.D. We applied a phase amplitude coupling with 2 different methods, one which was the typical, sorry, I'm forgetting the name. Sorry, I forgot the name right now. And the second, which is one that Tom Dupré-Latour and Alex Grandfort has divided in collaboration with us for, that is called the DAR model. Both quantification allowed us to show that there was a alpha-beta coupling, which you can see here on average across all participants. So what we were interested in was to see whether this coupling here was predictive of the duration, as some of the clock model would predict. And this is not what we found. What we found is that the strength of the coupling between the alpha phase and the beta power was predictive of the precision. So here you can see the coefficient of variation, which is the inverse of the precision, being strongly correlated with the, or negatively correlated, hence the precision would be positively correlated with the strength of the alpha beta power. So what we're trying to say here with these, in this series of cross-frequency coupling, basically is that on a per individual basis, what we found is, and these are actual data, the participant who shows a temporal precision that is very narrow, or a good temporal precision in his temporal estimates, is going to, he or she is going to show a very strong coupling between alpha and beta, whereas the participant who showed a very lousy precision in his temporal estimate will still show some significant coupling, but much lower than the previous participant. And this is irrespective of the accuracy of the participant. We've replicated since the same results in terms of the beta power n of the cross-frequency coupling in a temporal reproduction task in which you both encode and reproduce a temporal interval. And this time, when we look at cross-frequency coupling, what determines the precision is neither the encoding alone nor the reproduction interval alone, but the ratio between the reproduction and the encoding. So I think I will stop here perhaps because it's been already, I think, roughly 45 minutes. So I wanted to simply put this slide here because this is from a citation or a quote that we often see, and this is from Harvard alumni. I hope that perhaps the last thing I would show here as far as data is that I hope this talk went fast. The reason is that the more cognitive load, which is being represented here as a working memory load, the more time you lose, and so the more time flies, and I hope that's what just went through to you. And in terms of take-home message, basically mental time, in terms of mental time travel, was to show that we can have an egocentric ordering of events, arguing for the possibility of temporal maps in the brain. The metacognitive time with the argument that possibly a readout of state-dependent trajectories may help in evaluating how good we are in timing, and the motor time being an actual passive relief of inhibition. And to conclude on the first mention of Kinsborn and Dennett and the difficulty basically of addressing the problem of experience time versus objective time, the proposal here across these different studies was to try each time to take into account the time arrow, meaning the time dimension of the phenomenology, and trying to remap brain activity with respect to that reference, as opposed to staying in the reference of the events that we present to participants. And I hope this was somewhat convincing. And again, thank you to the contributors of this work.